This is Statistics 243 at Berkeley for Wednesday, November 12th. Huh? Yeah, because when I first set up the randomization, there were people in the class who have since dropped, and so now I'm just going with the same randomization but dropping people who.
Oh, I get it.
Yeah.
It's a good thing with the panel smaller, so the smaller chance of being high, right? That's like basically.
No, because he's smaller.
Right.
Although the class is smaller, but like I forget that.
All right, let's go ahead and get started. So I have a few more things I want to talk about in the simulation unit, and then we'll move on and start talking about optimization. And we'll be talking about optimization basically for a majority of the rest of the semester. So we'll be talking about the rest of this week, all of next week, and all of Thanksgiving week. And then there'll be a couple of shorter units during the last week of class. Okay, so we talked about rejection sampling last time, and this idea that if I have some density that I want to draw from, but I don't have any algorithm that will allow me to just draw from that simply, if I could come up with some other density that when I multiply that other density by a constant that is always above the density of interest, then I can go ahead and basically go ahead and draw from this G. Well, this is C times G, but I can draw from G, and then I can do a correction to basically exclude this area here. So that's all well and good, and it works well if you can come up with a good G where there's not so much space in here that you're not rejecting most of the time. Okay. So I don't want to say a lot about adaptive rejection sampling. I'll just mention what the idea is. But the idea of adaptive rejection sampling is to try and get around this problem that maybe you can't come up with a good G, and it might not be very close as an upper bound to the actual density of interest. So what you do in adaptive rejection sampling, this actually is generally used in, I'm not sure if it gets used outside of Bayesian statistics, but it's sometimes used in certain aspects of Bayesian statistics, is that if your density is something called log concave, so if you can take your density function f, and if you take the log of it, if it's a concave function, so then you end up with, this is the log of the density. So this would be the log of f of x. So this being concave means that if I take any 2 points on this curve and I draw a line between them, that line is always going to be under the curve. So that's the definition of concavity here. So the nice thing about having a concave function is, let's suppose I take a few points along the curve and I just draw the tangents to those points. So if I do that, the nice thing that this does is if I think about sort of following along these tangents until I get to the point where they intersect each other, like this, I've already got an upper bound for the density of interest, okay, because of the concavity. And so as you can sort of, the drawing I drew here, it already seems to be kind of close. But there's basically a whole algorithm, and I don't want to go into the details, where as you draw samples from this density, so you basically draw samples from this upper bound and do the same sort of acceptance rejection that we talked about for the regular rejection sampler to make sure that we're not including this sort of excess of points in these areas here. But the other part of the algorithm is basically that you add points as you go along such that you refine your upper bound. And so you might, for example, add a point here, and once I add a point there and draw its tangent, you can see now that if I trace out the upper bound, I've now got an even tighter upper bound on the function of interest. So that's the basic idea. It turns out you can, well, I don't want to go into this, but you only add points. There's sort of an algorithmic way to do this. You only add points in cases where there is sort of a large gap between the upper bound and the actual density of interest. And so as you move along, what ends up happening is that if I sort of redraw the log of the density, you end up having this sort of piecewise upper bound that very closely follows the actual density of interest. And these little pieces are basically from connecting together all of these tangents in the relevant for the relevant pieces of those tangent lines. For the adaptation, or yeah, it's basically just an adaptive procedure, and this whole thing is called adaptive rejection sampling. So it only works for log concave densities, but if you have a density that's log concave, it works pretty nicely. For those of you who are curious, the project last year was to implement an adaptive rejection sampler. So that was what I used as a project last time. Oh, and I should say the reason why having these piecewise linear terms as the upper bound is useful and makes it easy to draw from is once I have these piecewise linear pieces, in any given segment here, I just have a straight line. And if I exponentiate, that just means I have a piecewise exponential distribution. So each piece is its own little exponential distribution, and I can draw from those relevant exponential distributions easily because I can just draw by an inverse CDF from an exponential distribution. Okay, sort of broader interest, so we'll spend a little bit more time on it, is something called importance sampling. So the idea of importance sampling is, suppose I'm interested in estimating some expectation. So this just goes back to the notation I used at the beginning of the unit. I have some function of the data. This could be an estimator, like a regression, the MLE for a regression coefficient, or the MLE for some parameter in the distribution. If I want to know if I want to know the expected value of some function of the data, whatever any expected value of interest, I can just write this out as what is the expected value? Well, it's just the integral of this functional with respect to the density f. That's just the standard definition of an expectation. Well, if I were able to draw from f, then we've already seen in the beginning of the unit that my Monte Carlo estimator would just be to take the sum from I equals 1 to m of h of xi, where these xi's were drawn IID from the density f of x. But now we're supposing that it's not easy to draw from f, and therefore I can't implement this standard simple Monte Carlo estimator. So the idea again is to come up with some other alternative density that is easy to draw from and to use that in place of f, and then basically implement a correction to adjust for the fact that I'm not drawing from the correct density. So the first step in thinking about this is basically writing this out using this sort of trick here, which is I can think about multiplying and dividing by some density g of x, and that's not going to change the expression because that'll just cancel out. But I've sort of written it in what's supposed to be an evocative way, which is, let's look at this, and now I can think of this as being, well, this is basically an expected value of some new quantity with respect to a density g of x. And the idea is that I choose g of x such that I can easily draw xi from IID from the density g of x. So I want to choose a g that I can easily take draws from. So given that I now am taking draws from g, I can just come up with a Monte Carlo estimator for this new quantity here that I'm trying to estimate, which is the h times this ratio here. And so all I need to do is basically, here's my new Monte Carlo estimator. And you can think of this as that the f, for any given x that I draw, I can calculate the density of x under f, and I can calculate the density of x under g. And you can think of this as just a weight. So instead of taking an unweighted average of the h of x guys, in this case I'm just taking a weighted average of the h of x guys. And this is the same idea of why this holds in this case. Just the law of large numbers says that this thing will converge to that, but this thing will converge to this, and those two things are the same exact thing. Okay, so before we explore that a little bit, are there questions about that? All right, so one of the standard things that people talk about when they talk about importance sampling is what kind of G would you want to choose? And generally you would want G to be somewhat similar in shape and form to F. But one of the most important things is what I say here, which is, well, also we need the densities have common support. So we need to have them, if f exists on the whole real line, then we need to have g exist on the whole real line. Or if f is restricted to some part of the real line, then we need to make sure that you can draw g, that values of g, that g covers that entire portion of the real line. It could also cover other portions, but it has to at least cover that portion. Okay, so then I just want to explore this idea that this comment here that things can be badly behaved if we sample from a density with lighter tails than the density of interest. So suppose that we had G was something like a t distribution, or suppose that we had F was something like a t distribution. And I choose to sample from a G that has lighter tails. So let's say it's something like a normal distribution. It doesn't have to be exactly these, but just you can think of these as examples that illustrate the idea. Well, if we do that, we can draw out a picture of sort of what this procedure would look like. So I've got some F distribution that has sort of heavy tails. So here's F. And now I have some G distribution that has lighter tails. And now let's think about drawing a whole bunch of values from G. So most of the values of G are going to be sort of in the middle of the distribution. But as I occasionally get values of G that are somewhat out farther in the tail, let's think about what the weights for those values are going to look like. Right? So the weights are going to be F over G. And so if I get something that starts to be somewhat out in the tail, then my F value is then my weight is going to be F of xi over G of xi. And this is for an xi that's in the tail. Right, so this is going to be some large value divided by a small value. So any of these values that I get that start to get out in the tail are going to look like this. We're going to have a very large weight. And then the story is just that if you're taking a weighted average, and one or a few of the values have very large weights and the other values have much smaller weights, it's going to be a very unstable estimate of whatever it is that you're trying to estimate, because the thing that has the very large weight is going to have a really, really strong influence on the estimate. Right? And you can think about this as, well, okay, where I happen to draw, say, an x that was out here. Just by chance, it was right where it was. You know, I might have drawn it here, I might have drawn it here, it might not have even been in the tail at all. But it's sort of the exact value, the value of this Monte Carlo estimator, because this weight is going to be very large, is very sensitive to the exact h of xi that I get for that particular xi. So it's just basically a story of if you have a weighted average where you have a few very large weights, that's not going to be a very robust estimate. If you did the procedure over again, you wouldn't get that particular xi that had that particular very heavy weight. You might get a very different estimate of the quantity that we're trying to estimate. So in general, if you're doing this important sampling procedure, you generally want that G has a heavier tail than does F, as opposed to this reverse scenario here, which would be the very bad scenario of having F have a heavy tail and G have a lighter tail. And you can sort of think of what's going on here is that F says that occasionally you should sample out here in the tails, right? So we do want to draw samples from out there. G doesn't put very much weight out there, so it's unlikely that you're actually going to sample out in the tails according to G. So on those rare occasions when you do sample out in the tail, you have to upweight those values a lot because you're not sampling out there as much as you should be. So the whole idea of the weights is to sort of correct for this disparity between G and F. But once we're out in the tail, if G doesn't sample out there very much, then the weights are trying to correct for that. They're doing it this way where you get a really heavy reliance on those occasional observations that are out there. Okay, so any questions about that? Yeah.
So when you increase the number of simulations, like increase the number of M here, like help.
Yeah, increasing m is always going to help. But if you're in the situation where the tail of f is much heavier than the tail of g, even that is not going to solve the problem. You'd have to increase it so many that the amount of computation you have to do would be huge to try and make up for the fact that I'm getting an occasional value that has a very large weight. Other questions? Another way that you could think about this is the variance of my Monte Carlo estimator looks like this. And this is another way of just saying, as an equation, what I just said, which is I'm going to have a high variance for my estimator if this variance is large, and that will occur when I have, if I end up having this ratio be large in places where h is non-negligible. And so in this case, since f has heavy tails, that means h is non-negligible for sort of a larger part of the domain. And this is saying that the weighting that goes on for that part of the x domain is large, and that contributes to this high variance. The other idea I wanted to draw out here is this idea of you could sort of strategically choose where to put a lot of weight to get a lower variance estimator. So I think that's a useful idea just to draw out as sort of a general principle. So suppose that I wanted to estimate some mu hat, which is the probability that some random variable is less than some value c. So this is just another one of these estimators. I can express this as the expected value under some density f of an indicator function that x is less than c. Okay, so I've just taken a quantity that I'm interested in estimating and re-expressed it in terms of our notation of an expectation with respect to f for some function h of x. So suppose that, and this sort of is going to look sort of like the example we did last time with rejection sampling. Suppose here's c, and suppose I have some density f that has most of its mass bigger than c. Okay? So you can imagine that if I drew a lot of values from f, only a few of them would be less than c, and it would take a lot of draws to get a reliable estimate of what the probability of being less than c was. So another way of writing what my h function is my h function is just a uniform function, or it's just a uniform. It's just a flat function. Up. It's basically, well, it is an indicator function. It's just 1 for anything less than c, and then it drops down and it's 0 for anything bigger than c. So what I wanted to do here was say, what if we were going to design a function g that would be a low variance estimate, that when we use it with importance sampling would give us a low variance estimator of this quantity that I'm interested in. So I want to come up with a g. So I've already said that, we already talked about this idea that the variance of my estimator is going to be equal to okay, so if we sort of start to go back and pick this apart a little more, well, first of all, okay, as we increase m, the variance is going to go down. So that's Lay's point from before. We've already decided for this particular problem, we know what h is, and we know what f is. And so then the question is, what would I do to choose a g such that this quantity is small? So stare at that for 30 seconds or so. Feel free to confer with your neighbors and see if you can come up with sort of a general idea of what we want g to be like, or even sort of an idea of sort of what some picture of g might be. Okay, so thoughts?
So we're thinking that we put G where, make G bigger where H is big.
Yep.
And smaller when H is small.
Okay.
So
Right.
that it can balance out and the total variance will be small.
Right, so we know what H is, we don't have any control over that. So it's going to be large, I mean, large-ish. It's going to be 1 versus 0. It's going to be 1 someplace. We can't reduce H, we just have what it is, right? So this is going to be large in some places, namely less than C. So as Yue was saying, we want to make G small in those places so that it basically sort of cancels out with the H in those places. And it doesn't really matter how big H is in this part of the domain, because in that part of the domain, H is small. H is 0, in fact, in that part of the domain. So it doesn't really matter if G is big here or not. Okay, so that's definitely the general principle we want to follow. So what choice could we make, for example, for G to even be concrete about a G that we might choose? It has to be something that we can sample from easily. But what could we choose for G that satisfies that idea?
I just have one question. Does it mean that G has to be very similar in shape as F at the portion where it's before C?
It doesn't have to be similar in shape. We do want to make sure that it's not the principle from before, that we don't want it to be such that we get very high weights. So we don't want to have it be very small in places where we don't want it to have it be much smaller than F anywhere. At least anywhere where H is not negligible.
So the shape doesn't matter in this case of the shape of G?
I guess, yeah, I would say the shape of G doesn't necessarily matter all that much, except we wouldn't want if we wouldn't want G to be much lower than F here, because then what would come into play was the stuff we've already talked about. So any ideas of what we could choose for G? What's the simplest distribution we know, or one of the simple distributions that we know how to sample from? All right, so either a uniform or a normal distribution. Can it be a uniform distribution? Okay, why can't it be uniform? Because the support of F, as I guess I didn't say it explicitly, but it's sort of implied here, the support of F goes off to negative infinity. So there's no uniform distribution that I can choose that will have common support. If I tried to put a uniform distribution down like this, I would never be sampling out here, and that violates the rules. So it can't be uniform, but what if I just wanted to use a normal distribution? What would I do to use a normal distribution here? Yeah, choose a mean that's sort of over towards the left-hand side, right? So I could just choose a G, say. So this would be if I were to choose a G that were normal, that would mean that would be under the assumption that I sort of knew that F didn't have a particularly heavy tail. But if F didn't have a particularly heavy tail, then this should be fine. I could choose a G that was a normal distribution that looked something like that, and that should be fine. And you can sort of think intuitively about what's going on here, which is basically why I wanted to sort of draw out this example, is it's this idea of oversampling in places where, what's the wording I want to use here? Sort of oversampling in the important places, and the important places here are where H is big. Okay? So I'm going to choose my G to oversample over here, and it's going to undersample over here. And then by virtue of having, I guess I've erased it now, by virtue of having the weights, it's going to correct for the fact that I'm not using the correct distribution. But this basically concentrates the sampling in the part of the domain, which is the important part of the domain according to this function H. Okay, any questions or other comments about that? You can sort of think there's sort of an analogy here to if you were doing survey sampling and you were trying to oversample some small subgroup of the population where you want to get a reliable estimate for that subgroup of the population. But if you were just doing random sampling, you wouldn't get a large enough sample for that small subgroup to get a reliable estimate. Same sort of idea going on here is you're sort of oversampling in a certain part of the space to get a more reliable estimate. Okay. So I'm gonna. So I asked you guys to look over sections 4 and 5. A lot of these issues, the number of these issues came up when we talked about the paper. So I'm not going to talk about any of that here in class. So let's move on to the optimization unit. So this is unit 13. There'll be a couple more units after this, but they'll be short ones, as I mentioned at the start of class. All right. A couple of comments before, or actually one question and one comment. How many of you would say that you're familiar with Newton's method or Newton-Raphson for doing optimization? Okay, so a few of you. All right. So we'll certainly see Newton's method and a lot of variations on Newton's method in this unit. The other thing I'll mention is that we're going to see Taylor series expansions in a few different places to justify what we're doing in terms of Newton's method and in terms of some of the other aspects of what we're doing. So if you don't remember what a Taylor series expansion is from whenever you would have encountered Taylor series expansions, I guess some version of calculus, do go ahead and look back and just make sure that the idea of what a Taylor series is makes sense to you and is familiar to you. Okay, so just a little bit of notation. We're going to be doing a lot of work where we're making use of the gradient of a function and the second derivative matrix or the Hessian of a function. So the idea is we have let me step back a second. The basic story with optimization is that we have some function that we want to minimize. Okay? So here's our function f that we want to minimize. I'm just drawing this as a function of univariate input x. We want to find this point x that minimizes the function. But you can also think of this as being in higher dimensions. I could be working in 2 dimensions, and I have some shape, and I want to I have some function that lives lives in 2-dimensional space here, so it's basically coming up out of the floor. I want to find the point, in this domain, say the room, where the minimum of that function is found in 2-dimensional space. But it's the same basic problem here. So I can think about taking the gradient of f, which is taking the derivative of f at any point x along this curve. And I can also think about taking the second derivative of this function f at any point x in this domain. And if I generalize that to higher dimensions, then I'm thinking about taking the gradient vector, which is taking the derivative of f with respect to all of the coordinates x1 up through xp. And I'm going to also make a lot of use of the matrix of second derivatives, which I'll either call this sort of grad squared of x or h of x for the Hessian, which is another name for the matrix of second derivatives. So this is just going to be a matrix of all of the pairwise partial derivatives of f. So taking the second derivative of f with respect to x1 twice, or with respect to x1 and then x2, et cetera, et cetera. Okay, and then a little bit more notation. The idea is that we're going to be trying to find this point x star, which is the optimal point here, that is where the minimum occurs. And in order to do so, we're generally going to use some sort of iterative algorithm. So the idea is, if I could solve this problem in closed form and just do it via mathematics, in general, I would do it. But I don't have I don't have a closed form way of doing that solution. So the idea is I'm going to start with some starting value, and let's call that x0. And then I'm going to come up with some iterative algorithm that basically, hopefully, takes steps towards the minimum and converges toward the minimum. So the next step might be x1, then I might take a step to x2, and then x3, x4, x5, et cetera, et cetera. So I'm sort of overloading my use of the subscripting here. In this case, what I mean is this is the sequence of points that I'm going to go through in my iterative algorithm. But when I've been talking about it here, I was talking about it as the coordinates in my space. So hopefully it'll be obvious in the notation as I'm using the notation. I'm hoping it'll be obvious in which case I mean different things by the subscripts. But if you do have questions, if the notation is not clear, just stop me and ask me. Okay, so why is this important from a statistical perspective? Well, often the main case where we're going to be trying to optimize some function is we have some likelihood function or some penalized likelihood function or some other objective function that if we maximize it, will give us the value of the parameters of interest. So it might give us the maximum likelihood estimator, or it might give us a penalized maximum likelihood estimator, or some other estimator of the parameters that we're interested in. So in general, we're going to be taking, say, something like the log likelihood. We want to maximize that, but we'll usually talk about minimization. So we're just going to take the negative of the log likelihood, and we're going to minimize that, and that corresponds to maximizing the log likelihood. So just some examples of where we might try and find where we might be solving an optimization problem. We might have a generalized linear model like a logistic regression, and we might want to find the MLEs for that, and we'll do that numerically. We'll see how that gets done numerically. We might have a nonlinear least squares problem where we have the observations are normally distributed with some variance sigma squared, but instead of having x beta, some linear function in here, we have some nonlinear function g that depends on covariance z and depends on some coefficients beta, and we're trying to find the values of beta and the value of sigma squared that maximizes this normal likelihood. Or we might have some likelihood that has where we have some constraints on the parameters. An example of that would be the problem on problem set 5, where we talked about this idea of where I gave you this problem to work on of working with estimating regression coefficients under some constraints on those coefficients. Okay, so any questions about the setup here? Okay, so just going back to basic calculus, if we think about optimizing some function, if we think about finding a minimum or a maximum of some function f, that optimum is going to occur where the gradient is 0. Right? You can just see that here from this picture here. The gradient here at the minimum is 0. And if it's a minimum, it's going to be a case where the second derivative is positive, right? So that the acceleration or the change in the gradient is that the change in the gradient is positive. So that means that we've reached a minimum. And the analog in higher dimensions, if we have a function of more than one dimension, is that the Hessian matrix is positive definite. So it basically means if we think about optimizing, say, in two-dimensional space, if I think I'm at the minimum, and so here's the minimum, I have to be going up in all of the directions. So basically, what that is equivalent to is saying that the Hessian is positive definite there. Basically, that I sort of, in whatever direction I go, that direction is going to be going uphill as opposed to going downhill. Okay, let's see. Okay, so you guys can read that in terms of what I'm hoping you get out of the unit. So let's start with a particular example. So we're going to sort of build up where we're going to do a few examples of strategies for optimizing in a univariate function, and then we'll take those ideas and generalize them to multivariate functions. And a lot of the ideas a lot of the algorithms that we'll have in one dimension will also be useful as components of optimization in higher dimensions. Okay, so the first example, the first case I want to talk about is something called the golden section search, which is kind of a cool idea that with a little bit of geometry behind it. Okay, so we're going to assume that we have some function f, and we know the minimum lies between points A and B. So we're just searching in this domain of x between A and B. And we're also going to assume that this thing is unimodal. Okay, so it only has one minimum in this area. So I'm ruling out problems where things look like that because here we have two critical points, and that makes it harder to find the actual global minimum. So for the sake of what we're doing here, we're going to assume there's a single global minimum, and therefore only one local minimum as well. Or not therefore, but we're going to assume there's only one local minimum, and therefore that is the global minimum as well. Okay, so the idea of doing this is we're going to start by saying, okay, I can evaluate. Suppose I choose 2 points here, x1 and x2, and I evaluate the function f for those 2 points. So I might find out that those are the two values of those are the values of the function at those 2 points. So what does that do for me? That rules out that the minimum, it says the minimum can't be over here, because I made the assumption that the function is unimodal. So if there was a point, if there was a point over here that was lower than this, that would violate my assumption. So what I've done by evaluating f here and here and finding out that this is lower than this is it says I can exclude this area here. So I've excluded a third of the domain if I've sort of equally divided this here. Well, okay, now I can think about the second iteration of this procedure. And I can think about, well, what if I add a third point in to try and eliminate even more of the domain? Okay. So I might choose x3 to be here. And suppose I find that f evaluated x3 is here. Well, then I've sort of gotten lucky because that says, well, now I know my minimum is between x1 and x2, and I've actually ruled out half of the remaining domain by having gotten lucky and chosen my x3 to be in the portion where the minimum is actually found. But suppose just arbitrarily, since I don't know until I've actually chosen x3 and evaluated f, suppose that I chose x3 to be here, and I got that the value of f was up there. How much of the space have I eliminated in this scenario here? Yeah, so I've only eliminated this because there's nothing that said, I could still have the minimum be here and satisfy unimodality, or I could have the minimum be in here and satisfy unimodality. All I know is that it's not over here. Okay? So I could have either gotten lucky and eliminated half of the remaining space, or I could have gotten unlucky and only eliminated a quarter of the remaining space. So by virtue of how I've sort of set this up, I tried to start to be smart by saying, well, let me choose these so that I'm going to automatically eliminate either this third of the space or that third of the space. That worked nicely in the first iteration, but the next iteration around, I realized, I'd like to be the idea is that the optimal thing to do would be to eliminate a constant fraction of the space at every iteration. And this doesn't satisfy that criterion. So the golden section search is set up to basically cleverly eliminate the same proportion of the remaining area, the remaining length at every iteration. So the idea is it's set up like this. So suppose I draw out my picture again. I have from A to B. And now I think about choosing, do I want to call this x1? Yeah, I guess I might as well. I'll call this x1. So let me call this 1. So whatever the length of A minus B, of B minus A is, let me call this length 1 minus phi of that. And let me call this length sorry, I'm using, just so I don't confuse myself, let me stick with the notation that I was using in my notes. Okay, so this is the phi proportion of the interval between A and B, and this is the 1 minus phi proportion. So if I do that, I can then think about, well, there's another point over here where the length from here to here and the length from here to here are the same. So this is also 1 minus phi. And as a result, just by simple arithmetic, the length of this interval in here is 2 phi minus 1. So now, if this is x1 and x2, and I do what I did up there, I'm either going to eliminate this portion, or I'm going to eliminate that portion. So I'm always going to eliminate 1 minus phi out of the total length of 1 here. Okay, well, it's not really 1, it's b minus a, but you can rescale and normalize and think of it as being 1. So that's the proportion I've eliminated in the first iteration. And now if I think about, okay, well, it doesn't really matter which one I consider to have eliminated. Let's assume that I've eliminated this portion of the space. And now I think about placing my new point x3, just like I placed my x3 up there. Well, the place I'm going to put x3 down here looks like this, such that that this is also, let's see, is this going to work? So this is,
Scale by x, whatever mine
Yeah, so the total length is going to be 1 minus phi plus 2 phi minus 1, which is just phi. So that's the total new length. And the idea is I should be eliminating, is this not working? Oh, okay, because I put my point in the wrong place, sorry. All right, let me draw this picture again. So the idea, and I've sort of drawn it in a bad way in terms of proportions relative to what phi is going to work out to be. So let me draw this in a way that's a little bit easier for me to work out here. Okay, so this is now 2 phi minus 1 here. This is the 1 minus phi that I eliminated. Instead of putting x3 in here, because this is going to turn out to be smaller than this, I'm going to put x3 over here. That was why I was getting fouled up. So if I choose x3 over here in such a way that this is 2 phi minus 1, now I've got another one of these symmetric situations where, depending on what f of x3 and what f of x2 are, I'm always going to eliminate 2 phi minus 1 out of this whole length here. So if I eliminate 2 phi minus 1 out of the total length is still phi, and this is 1 minus phi that I originally eliminated. The idea is this is how much I eliminated, the relative proportion I eliminated after the first iteration. This is the relative proportion I eliminated after the second iteration. And if you keep working this through, you can basically just see that when you do this again, you can do the same thing at the third iteration, the fourth iteration, and so on and so forth. So how do I decide what phi is? Well, if I think about this is just going to be a quadratic equation. Right? I just take 1 times 2 phi minus 1 equals phi times 1 minus phi. So 2 phi minus 1 equals phi times 1 minus phi. And I just solve that quadratic equation for phi. And so phi ends up being this sort of number that also appears in like some classic Greek geometric settings. This is called the golden ratio, and the number is about 0.62. So what this says is I basically eliminate 38% of the remaining interval at every iteration that I take. And this is basically, if you sort of think this through, this is basically the best we can do under this situation of wanting to eliminate the same proportion of the interval at every iteration. Okay, so questions or comments about that?
So how does this compare to bisection?
That's where we're going next.
Oh, sorry.
Yeah. Other questions? Okay, so that's so I laid that out, a little bit of the details here of what I just talked through. Okay, so Guang's question was, he knew of the existence of something called bisection, which is actually more efficient than this. So part of the question is, well, why would we even talk about this if bisection is more efficient? Well, the idea is I didn't actually make any assumptions. The assumption that I made for doing this kind of golden section search was I just assumed basically that this was unimodal and that the minimum I'm interested in lies in this interval from A to B. You'll notice I didn't use any information about derivatives of the function here. I just used the fact that I could evaluate the function and find out what's the f here, what's the f here, what's the f here, and so on and so forth. So the idea of bisection is that if I am willing to assume the function has a first derivative, then I can actually use the information from the first derivative to remove more of the domain at every step. So by having some more structure in the problem and making this assumption and assuming that it holds, I can actually eliminate more of the interval at every iteration and come up with a more efficient procedure. So that's what bisection is. And so the idea is that we're going to start with A and B, and I'm still going to have this assumption of unimodality. So what I'm going to do is I'm basically I'm going to take a point right in the middle. That's why it's called bisection. I'm going to take this point in the middle, and I'm going to go figure out what is the value of the derivative at that point in the middle. Okay. So if I see that the derivative at this point in the middle is negative, that the function is going downhill at this point, then I know the minimum has to be over here. If I saw that it was a positive derivative, then I know that it has to be over here. Okay. And so you can see right away I've eliminated half of the space just by knowing the information about the derivative. Okay. And so basically I proceed onwards. I now choose, if this were positive here, and I choose this one, I now take the gradient here, and I say, well, what's the gradient here? Well, if the gradient here were negative, then I know that it's going to be in here, and I've removed this half of the space. If the gradient here were positive, I would know that I have to be in this portion of the space. So basically, at every iteration, I am eliminating half of the domain. And that's basically what is written out in terms of the notation there. So I think we're getting close to being out of time. Yeah. Let me see. I forget if I have an example that I was going to show for that or not. Okay, I guess I didn't actually write out an example for that. Okay, so any questions about that? Okay. So those are two fairly basic methods where we're sort of building up from assuming less to assuming more. The next thing we'll cover next time is the basic Newton's method, also called Newton-Raphson, which is also, for the moment, we're going to be talking about it in one dimension. And that's going to converge even faster than this bisection method, but it also has some problems that could cause it to go badly wrong in certain situations. So it's less robust, but it's faster when it works, and we'll see that next time.